So random variable, formal definition. It's a function. It's a function that assigns a numerical value to each possible outcome of a random experiment. In other words, it's a mapping function that maps your set of all sample space, which is denoted by omega, to your real number, which is right here. It's a mapping function. Now, if you're confused, just like this guy over here, then this session is for you. Here, I will explain you what a random variable is through examples. Random variable. Plain English. It is a numeric variable that represents the outcome of a random experiment. Its value is not fixed but depends on chance. These variables, they may change randomly from one experiment to another. And generally, you use letter X, capital letter X, to denote random variable. For example, let's say you roll a dice right here. In this case, your X, your random variable X could be 1, 2, 3, 4, 5, or 6. How about you standing on a toll and you want to count how many cars are passing through a toll in 1 minute? In that case, your outcome could be 0, 1, 2, 3. It could be any number of cars passing through the toll. So that is your random variable. Well, maybe you're measuring the temperature of a room. Well, again, your outcome in this case, which is your random variable, x, could be 10.3, it could be 4, 5.34, it could be taking any value. These are your random variables. So there are two types of random variables, discrete random variable and continuous random variable. So let's focus on discrete random variable first. So these are the random variables that can take values like which are discrete in nature. For example, -3, -2, -1, 0, 1, 2, 4, 8, okay, and so on and so forth. These are your discrete numbers. In other words, these are the variables that can only take finite or countably infinite number of specific values. So let's take a look at an example. Let's say you flip a coin 3 times and you want to count the number of heads. So when you flip a coin 3 times, what are your outcomes? What is your sample space? Well, this is my sample space right here. Okay. So I'm representing this sample space through a Venn diagram. So this is my head, 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 my head, head, tail, my tail, head, head, tail, tail, and so on and so forth. Now, the number of heads, okay, let's say I represent my number of heads as x. So my x can be 0, 1, 2, 3, because that represents number of heads I can get. So if I get head, 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 what is my number of head in this case? Well, you can map this. Okay, if you come over here, the answer is 3 heads right here. Okay, how about if you get head, head, tail, or tail, head, head, or head, tail, head? Well, this one gets mapped to right here, number 2, because there are 2 heads. And same thing with this right here. This one gets mapped to 1 head, okay, because there is only 1 head over here. And the last one, tail, 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 there is actually no head over here. So this one gets mapped to 0. So x can be 0, 1, 2, 3. And what exactly x is doing is basically, think of this as a mapping. It's mapping your sample space to a number on your number line. So now let's take a look at an example of infinite discrete values. Let's say you're sitting in a park in the middle of a night and for some reason you want to count stars. I don't know why, but maybe you do. So your outcomes in this case are all possible numbers of stars in your region. You can have 0 star, 1 star, 2 star, 3 star. It can have any number of stars. So in this case, my sample space right here would be this all star right here. Okay. Now, in this case, x can be represented as the number of stars in a selected region. So let's say you select a region. You select this region right here. Okay, let's say you select this region. So in this case, the number of stars in this region, that would be your x. So in this particular instance, I have 3 stars. So in this case, this region gets mapped to 3 right here. How about this right here? Let's say you select this region. Well, this one has 6 stars. So this one gets mapped to 6 over here. So this is an example of an infinite discrete values. Here your x is mapping your sample space omega to set of discrete values on number line. So this is an example of infinite discrete values. Now let's take a look at example of infinite discrete values. Let's say you keep tossing a coin until you get the first head and you want to count how many tosses you did before you get your first head. That's the experiment you're doing. For some reason, you want to do that. So in this case, each outcome represents the trial number on which the first head appears. So in this case, my sample space is going to be 1, 2, 3, 4, 5. What do you mean? What do I mean by this 1, 2, 3, 4, 5? Well, let's see. Let me explain you. Let's say you toss a coin 1 time. Well, you get a head, right? You get your head and you're good. So this is what this 1 means. Well, let's say you toss a coin. You get tail. All right. You didn't get the head. So you toss it again. Well, now you get the head. So in this case, your number would be 2. This would be 2. This one was 1 and this is 2. Now you do it again. Well, you get tail. The first toss you get tail, then you toss it again. You get tail, all right. You didn't get the head, toss it one more time. Oh, look at that. Now you get the head. As soon as you get the head, well, this becomes 3 right here. So this is what 3 comes. And I can keep going like this, okay? 4, 5. So what this basically represents, 1, 2, 3, 4, 5, this represents the number of tosses needed before you get your first head. Okay, so let x be the number of tosses needed to get the first head. Now in this particular instance, your sample space and your x is exactly same value. Okay, so x in this case can take any positive integer value. It can be 1, 2, 3, 4, 5. So if you think about it, let's say I'm representing my sample space through my Venn diagram. So this is my 1, and 1 is getting mapped to 1 right here. Okay, 2 in this case is getting mapped to 2 right there, and 3 is getting mapped to 3, and 4 is getting mapped to 4, and so on and so forth. So this is an example of your infinite discrete values. Now let's take an example of negative random values. Let's say you're gambling on a coin toss. Okay, you flip a coin 3 times. Okay, you flip a coin 1, 2, 3, 3 times. If you get 2 heads, then you will receive $1. Otherwise, you're going to lose $2. So my sample space in this case consists of head, 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 tail, so on and so forth. So this is my sample space right here. Okay, I'm using my Venn diagram to represent my sample space. So if I get head, head, head right here, okay, then I lose $2, right? I have to give $2. So it's mapped to 2. Same thing with tail, tail, tail. If I get tail, 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 it's going to get mapped to 2. What about head, tail, tail? Again, mapped to -2, okay? So all these values basically mean that I have lost $2. On the other hand, if I get head, head, tail, or tail, head, head, or head, tail, head, in this case, I win $1 because over here I'm getting exactly 2 heads. So my x in this case would be -2 and 1, which would be this value and this value. So think of x as a mapping function over here. Let's say you roll a fade die once. In this case, the sample space consists of your 1, 2, 3, 4, 5, 6. This is my sample space right here. Now let's say your random variable, I define my random variable as the number shown on the die when it is even. Otherwise, it is 0. In other words, if you get 1, 3, 5 on your die, when you roll your die and you get 1, 3, 5, then your x is going to take the value 0. On the other hand, if you get 2 on the die, your x is going to take value 2. If you get 4, it's going to take the value 4. And if you get 6, it's going to take the value 6 right here. So my x can take these values 0, 2, 4, 6. Let's say you roll 2 dice and you add the numbers on the pair of dice. So here, my sample space consists of all possible outcomes. In this case, you can get 1, 1, right? 1 and 1. You can get 1, 2. You can get 1 on this dice. You can get 2 on this dice. You can get 1, 3. 1 over here, 3 over here. So I can get all, basically you're going to get all 36 different possible ways, okay? So I list all 36 different possible ways that you can get 2 numbers on these dice right here. Okay, if x is the sum of the numbers on the pair of dice, then your x can take these values from 2 to 12. Let's understand this through a Venn diagram right here. This is my Venn diagram. So if you start with the smallest number, 1 and 1, okay, let's say you get 1 over here and you get 1 over here. So you add 1 plus 1 and the answer is 2. So this 1, 1 gets mapped to 2 over here. Okay, this 2 right there. Well, how about this one? If you get 1, 3, okay, let's say 1, 3, or you get 2, 2, okay, or you get 3, 1, okay, 3, 1. So these ones, 1, 3, 2, 2, and 1, 3, these ones, they get mapped to 4 because when you add these elements, 1 plus 3 is 4, right? 1 plus 3 is 4, 2 plus 2 is 4, and 3 plus 1 is 4. So all these elements, they get mapped to 4. And let's take another example. Let's look at this one right here. So this is 6, 5, and 5, 6. So if one pair gets 6, right, one gets 6, other one gets 5, and one pair of die gets 5 and the other one gets 6, both these elements, they get mapped to 11 because 6 plus 5 is 11. Okay, so basically this is what's happening over here in this mapping. 1 1 gets mapped to 2, 1 2, and 2 1 gets mapped to 3, 1 3 2 2 gets, and 3 1 gets mapped to 4, and so on and so forth. So in this case, if you think about it, your x, this x right here, is a mapping function. It is mapping elements from your sample space to your numbers, going from 2 to 12. Counting defective items in a batch. Let's say you have a batch of 4 right here. Here, my sample space consists of these elements. So for example, this could be defective, this could be defective, this could be defective, this could be defective. So this is one element of my sample space. The other one could be triple DN, right? Defective, 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 and not defective. Or it could be right here, defective, okay, defective, not defective, and defective. And I can keep going like this. So you in total, you're going to get 64 different outcomes. D refers to defective and N refers to non-defective. So in this case, the number of defective, right? So if you think about it, your number of defectives can range from 0 to 4. So for example, if you get DDD, right? In this case, if it's DDD, like all 4 defectives, then your X will take the value of 4. In other words, your X maps this DDDD to 4. Same thing with this. If you get 3 defectives, like the DDDN or DDND or DNDD, in other words, 3 defective. If you get 3 defectives, then all these elements from your sample space, they're going to get mapped to number 3 by this X right here. Okay, same thing over here. In this particular instance right here, I only have one defective. That's it. So all these elements, there's only one defective. So this one gets mapped to number 1. So X in this case is a mapping function. And what is it producing? It's producing 0, 1, 2, 3, 4. Picking a person's age expressed in years in everyday use, like let's say when we count somebody's age, generally we use years. Okay, so this in this trial, in this example, I'll be using age as in years. So your sample space would be anywhere between 0 to 120. 0 could be, let's say you pick up a person on the street and that's a 2-month-year-old baby. You can say that's a 0 year. Okay, you can consider that as a 0. 120, maybe there's a guy you just happen to come across, he's really old. Okay, so representing x as age, we see that in this case, any discrete number between 0 to 120 is possible for your x. Okay, so x can be any one of these numbers. So 0 gets mapped to 0, your 1 gets mapped to 1, 2 gets mapped to 2, 3 gets mapped to 3, all the way up to 120 gets mapped to 120. So your x is in this case is mapping your sample space to your discrete numbers and your real number. And your numbers are anywhere between 0 to 120. By the way, in this case, your x and your sample space are identical, are same.